Right from the back, so we can start. Today we will discuss dust and ices, and I will introduce a little bit the formation of protoplanetary disks that we will look again in more detail after we do the molecular lines, and we'll discuss a little bit what we can learn of disk population and the infrared excess of this from the infrared excess of disks. Okay. Few notes on the feedback that I got yesterday. Most of you asked for more details on the uncertainties in the age determination and what is causing it, and the effects of variability. There are two key things. I've added a few things to the Facebook page, but there are two key things that I think you should be looking at. There is one great Protostars and Planet 6 review on determining ages of young stellar of stars in general, but young stellar objects in particular, and discusses a lot of these things. And then the discussion in Baraf et al. That was on one of my slides yesterday is really focused on the effect of the initial conditions on the tracks. So those are the key reference that you want to look at if you want to understand the details of this. Okay, so let's go back to my thread here, and today we will look at the dust first, and then see how the various phases appear due to the presence of dust around the young stellar objects. But first we go into some details about interstellar and circumstellar dust. Phil has already discussed some of this. Basically, what is important for the dust is that the dust essentially absorbs and reprocesses the radiation. That's the relevant part for what we are doing. So when you have a dust distribution around a young stellar object, be it a disk, an envelope, or whatever, you have basically to solve for the transport of radiation and the balance of this heating and cooling of the dust. And what you have here is just a simple formula that you have for the optically thin case in which the dust is heated directly by radiation and is cooling, emitting radiation at its own temperature isotropically. And so basically the equilibrium temperature can be solved through the equation. And if you basically consider this grain of dust at a certain distance from the star, you can estimate its temperature based on the stellar temperature and the distance from the star. Okay, this is telling you simply how this dust grains is being heated. This is for the optically thin case. Okay, so the key thing obviously in this, let's go back. The key thing on all this is the dust opacity, and so I'll spend some time in the dust opacity. So this is the dust opacity that is derived for interstellar grains. So it's not exactly our case. The key feature is that it has a high cross-section, so a lot of high absorption in the optical ultraviolet. And then this falls down, the cross-section falls down at high energy and at very low energy, so in the infrared and in the millimeter. Okay, so these are for, as I said, the interstellar medium dust. So these are small grains composed mainly of silicates and carbonaceous material. The silicate feature is the one that you see here at 10 microns, essentially, and the peak here at here is due to the carbonaceous material, essentially, in the ultraviolet. When you consider grains that are relevant for us, so in the dense regions of molecular clouds or in disks, in the dense regions of disks, you basically have grains that are sitting in a high density, low temperature environment most of the cases. And so you cannot simply assume that they are bare silicate or carbonaceous grains, but what happens is that the surface of these grains is basically becoming a surface where you can have condensation of ices. And so basically you are, as the temperature goes down, you are coating the dust, the inner silicate dust grain with species that condensate on the surface of the grains. So for example, if you go from say from the sublimation temperature of this dust, which is of the order of 1500 Kelvin, and you start cooling it down, then when you cross the water condensation temperature, so the snow line, you go below 150 Kelvin, you start to coat these grains with water ice, and then as you go to cooler and cooler temperature, other molecules will go onto the ice surface. So you will have carbon monoxide, methanol, carbon dioxide, and so on. These simple molecules that are present in molecular clouds, in the diffuse in the less dense phase of the molecular cloud. As you go into the denser and denser phase, they get onto the dust grains and onto the surface of the grains. What happens when you are close to a young stellar object? So when you start forming the star, and the star starts to have a feedback on the material around it, is that you start processing this icy mantle. And so you have, again, say, in the outer region, in an envelope or in a disk around the star, around the young star, you have these icy grains with the inner core and the ice envelope and the ice mantle. The ice mantle, which originally contains relatively simpler molecule, is being irradiated by the radiation from the central star, and chemical reactions can happen in the solid phase on the ice because of this irradiation, and so you form more complex molecules like formaldehyde and more complex organic molecules. Okay, and these complex organic molecules can then be released again in the gas phase if the grain is heated to a temperature which is high enough to sublimate essentially the mantle, or whether a shock creates the sublimation by destroying the grain. Okay, these processes are studied in laboratory experiments, and so here are some examples of what can happen. If you take, for example, this case here are examples of how a nice compound, which is similar to what we think these pristine ices are, is being irradiated for a period of time with a certain dose of radiation, and then is sublimated and checked essentially what is produced on this grain. So here you have, for example, a CO ice. The blue line is the original ice that contains mostly CO and CO isotopes, and then you process it, and you find that you create more complex molecules with several carbon atoms and several oxygen atoms. Of course, you start only from CO, so you end up only with molecules that contain carbon and oxygen, okay? In this case, you start with a methanol compound, for example, so an ice that contains CH3OH. You irradiate it, and you produce essentially, mainly you produce formaldehyde and some other complex alcohols and molecules. If you go even beyond this, so you get a more complicated ice containing nitrogen compounds, so for example N2 and 2H3, which are forming a gas phase and then can go onto the ices, then CO, then methanol, and you do this processing. You can even create something that is even more interesting from a prebiotic point of view, because you can create from an ice that originally did not have it, you can create an ice that contains amino acids, for example, okay? So this processing of the ice grains is important in creating the complex molecules. And one thing that I think I will go back at some point tomorrow if I have time is that this is in an early stage of comparison with the observations. I mean, how you can create this very complex molecule and return them into a stellar medium. But it's possible to do some comparison. Here, for example, you have from this type of experiments, you have the abundance of formaldehyde over the abundance of methanol as a function of time, both in an ice that contains only methanol, which is relatively unrealistic, and an ice that contains CO and methanol, which is more realistic for interstellar ices. And you see that as time passes, so as you increase the dose of radiation onto this object, essentially you form more and more formaldehyde at the expense of methanol to some extent. So a measurement of the abundance of these molecules in the ice, in the interstellar ices, can tell you how much the grain was processed, and this can be checked observationally if you do things properly. We will get to that in a second time. But let's stick to the solid phase at the moment, so to what can be observed of these ices, and how these are observed when they are in the solid phase. So they are normally observed due to the opacity, excess opacity that they provide in certain features. So, for example, if you have a star within an envelope that contains ices, okay, your stellar spectrum that is generated here as a stellar photosphere goes through this dust with ices and then is absorbed. And then in the end, you observe a spectrum that contains features, and these features, well, you have a general attenuation because of the dust opacity, plus you have attenuation from features, which are the ices, tells you about the ices on the surface of these grains. So this is just an example, okay, of the observation of one giant star behind a dense molecular cloud, okay? And you basically see that there are two effects. One effect is the general extinction, which is the red, what the red curve would be if you take the spectrum of the star and you extinct just for bare silicate grains with no ices. And you see that there is some excess opacity at certain wavelengths. And these opacities at these wavelengths you see are labeled here, for example, the CO2 ice feature, the water ice features, and the silicate, well, this is the silicate from the inner silicate material, okay? But basically, you see the ices in absorption, essentially, and you can compute from the optical depth, you can get an estimate of the abundance of these molecules in these ices. So these are examples from, I forgot to put the reference, from Oberg et al. I'll add them to the slides. Where you see observations of a number of objects in the mid-infrared with Spitzer spectroscopy, essentially, and you see the ice feature measurements and the abundance of different organic compounds as compared to water. Okay, so the reference abundance is the abundance of water. So this is all referenced to the optical depth of the water line. Okay, and you see that essentially typical interstellar ices contain typical interstellar grains, in dense molecular clouds, are coated by an ice layer that contains water, and roughly speaking 30–40% as compared to water of carbon monoxide and carbon dioxide. These things, let's focus on the low mass case only, because these are the ones that we are considering now. And also contain some lower abundance, but still between 5 and 10%, let's say, of this is not CH3CN, sorry, should be CH3OH, methanol, ammonia, and methanol ice. And basically, from the processing of these ices, you might expect to produce more complex molecules, as I illustrated in the laboratory. And I think the next frontier for these studies of ices will indeed be to go and be able to check what kind of molecules are produced really in this region. And we will get to that tomorrow, I think. If you consider these dust grains into molecular clouds with their ice coatings, you can compute their, the opacities that are a little bit different than the ones that I showed for the interstellar medium grains. And the factors, because they are different, are two. The first one is the presence of ices. And you see the effect of adding layers of amorphous carbon and ices on top of the silicate core in this plot. So these are opacities from the infrared through the millimeter, computed by Ossenkopf and Henning. The black line is the silicate bare grains, essentially, with separated amorphous carbon. And the others are opacities computed adding amorphous carbon layer and ices. And you see that, well, the ice features obviously appear. This is the water feature that you saw in absorption in the spectra. And the slope of the opacity at long wavelength is slightly different. Another important effect that you have in the dense regions of molecular clouds first, and this is what was computed here, is the fact that you start, when you basically the density increases, the collision among grains become important, and the grains start to grow, as was discussed by Willy yesterday. And so this growth of the grains produces essentially a variation of these dust opacities. Per cui, for example, here you have in the dark, in the full line, the opacities for dust that is not grown. So this is the standard distribution in the interstellar medium with two different compositions, but essentially not grown dust. And the others are dust coagulated because of this process of coagulations into dense cores. And you see that there are differences, especially at this level of growth, which is still moderate. The main differences are in the millimeter and in the near infrared, but they are not. And in the feature of the silicates, you see that the feature is less pronounced. In the non-grown dust, the feature is higher than in the grown disk, in the dust. Okay. Now, in a disk, you expect this process, as was discussed yesterday, to be even stronger. But let's first look at. This is the 10 micron silicate feature. This wasn't supposed to work like this. Okay, this was supposed to do this. Okay, if you have, this is an interstellar medium 10 micron silicate feature, which is relatively narrow and peaked. And if you grow grains, essentially, and you crystalline them, so you change a bit the morphology of the grain due to processing, then what happens is that the feature becomes broader, a little less pronounced, and with a set of peaks that are related to the different crystalline things, Forsterite versus the other forms. Okay, so in principle, this is a probe that you can use and has been used to quantify the level of processing of the dust that you are observing, okay? This still is for grains that go up to 1 to 2 micron in size, okay? The interstellar medium grains are typically sub-micron size. When you grow them moderately into cores and disks, you get to this stage here, but obviously you are still fairly away, a little bit away from the planets there, so you have to grow a little bit more. And this is an example of how this is just for simple grains without ices, but just to illustrate the point, if you do grow the grains from the interstellar medium size to larger and larger sizes, you see that you start essentially to modify the opacity at wavelengths that are comparable with the size of the grains. That makes sense, no? For grains that are much larger than the wavelength at which you are observing them, the grains are essentially black screens, while when they are smaller, they interact with the radiation. So that makes sense intuitively. So if you increase the size of the grains, you see essentially this effect. You are washing out the features, and if you end up with fairly large grains, okay, 1,000 micron grains, then you basically see that your opacity is essentially gray because at these wavelengths, because you are observing a wavelengths that are smaller than this thing. Okay, so potentially this is a very good probe of tracing the growth of grains. So the process that was discussed yesterday. Okay. The other thing that you noticed from here is that the absolute value of the dust opacity coefficient, which is cross-section per gram of dust, okay, is going down, obviously. So you are compacting in larger and larger volumes, so the volume for the surface gets larger, and so you enclose more mass in the same opacity to some extent. So you are tracing, you need more mass to get to the same opacity to some extent, okay? Now, the situation is not that simple because you don't have a single grain. You don't have just 1 micron grains or 10 centimeter grains. You have all grain size distribution when you grow grains. So you have to compute the opacities for grain size distributions. And also the tiny details of what I have shown, as I'll show in a minute, depend a little bit on the properties of the dust that you are using. But in this busy graph from Bruce Drain, you basically see that in the sub-millimeter regime, here you have the wavelength and the frequency. So from, say, here is 1 terahertz, so 0.3 millimeters, and here is 3 millimeters, 100 gigahertz. In this frequency range, the interstellar medium grains would produce a dust opacity coefficient per gram of dust that is essentially a power law of index. So the dust opacity goes as frequency to the beta. Sorry for missing the Greek letters here. But this exponent is of the order of 1.7, roughly speaking, for the interstellar medium composition of grains. As you start growing these grains, so the largest size, okay, the largest size of the grains grows. And as you do this, essentially this slope changes, so the beta changes, and it goes to more and more gray opacity. It doesn't get all the way to full gray opacity because you still have some small grains in your compound, but the overall shape changes, okay? So this is a different way of showing exactly the same thing. You can plot the dust opacity, the value of the dust opacity at 1 millimeter, for example, which is here, okay, roughly speaking, 1 millimeter. And this beta index as a function of the maximum grain size for different values of the of how you distribute the grains in your grain size distribution. You assume this to be a power law from small to larger grains, starting from one small grain, ending to a large grain, and this power law essentially is telling you how many large grains you have per small grains, okay? What's the balance between large grains and small grains? If your power law is very steep, this means that you have a lot of small grains and very few large grains. So the small grains dominate the opacity. The opacity doesn't change essentially as you increase the size of the largest grain, okay? And beta also doesn't change appreciably. If you go to shallow grain size distributions, so this means that the relative number of large grains with respect to small grains is a little bit more important, still not dominating, but a little bit more important, then obviously these grains start to dominate the opacity. And so you see a deviation of from the small grain opacity, and basically this beta index, as you compute, for example, between, well, in this case 1 and 7 millimeter, but across the millimeter range, let's say, becomes to go down, essentially, to go down to a small value, okay? We will go back again to this tomorrow for the measurements of grain size distributions in disks, but here I wanted to show you how this index essentially depends on your composition of the dust grains, okay? And you see that if you take compact bare grains, which is the simple thing, no ices, just compact spheres, then there is a very nice dependence, and as soon as your grain size goes above the wavelength, so 1 millimeter is here, so as soon as you go across your wavelength of observation, the opacity essentially becomes gray, and you can measure directly the size. If you include ices on your grains, the net effect, apart from adding some features, the net effect is that essentially you have a larger grain, but that corresponds essentially to the opacity of a slightly smaller bare silicate grains. So basically you are shifting this beta curve in this direction, okay? If you add porosity here means the fact that you have vacuum inside the grain, so the grain is not a spherical block, but it contains, as it growed yesterday, they can grow in a fluffy way. Then this is your way of computing this. This again implies that for a given value of beta that you observe or that you measure, this corresponds to grains that have grown to larger sizes, okay? So the bottom line of this is that if you don't know exactly the composition, and it's very difficult to know it, obviously, measuring a low beta value, in some sense, is telling you that the grains have grown, no? Because you cannot produce a low beta value with small grains, but cannot tell you precisely how large are your grains, because that depends on the details of the dust that you are using. Okay, so a short summary on the dust. One thing that I have skimmed through, I realized, is that you can use the dust as an excellent probe of mass because basically if you know the dust opacity coefficient and if you measure the emission and you know the temperature, then from the dust opacity coefficient you can derive how much mass is needed to provide the amount of opacity that you see. But obviously this works only if you're optically thin, because if you're optically thick, it doesn't work, obviously. And you need to know the dust opacity, as I just said. Dust composition and shape affect the opacity per gram of dust. So the uncertainty in principle can be very large, but in practice for all reasonable grains, composition and shapes, this is relatively understood within a factor of a few, so the absolute value of the dust opacity normally is not, we don't think there are two way off when we speak in terms of dust opacity per gram of dust, okay? Then there is another step if you want to go to measuring real masses, because your mass in molecular clouds and disks is almost always dominated by the gas. So essentially, typically, in molecular clouds and in the stellar medium at least, you have gas accounts for 99% of the dust mass. So essentially, the way it works of using the dust emission to measure the mass of say, a core or a cloud is to measure this amount of dust from the emission and then applying a factor of 100 to the measurement to derive the total mass. Obviously, this can be tricky, especially in a situation like the one in the disks, where there are a number of processes that favor the decoupling of certain type of dusts with the gas. And so you are, at some point, especially if you decouple the large dust grain from the small dust grains and the gas, then if you observe the large dust grains, they are not necessarily tracing the gas anymore, okay? So this is a tricky business for disks, and is one of the. We will get back again to this tomorrow, and is one of the key uncertainties that we are still working on. And okay, and finally, the dust opacity and also the features are a good probe of the dust processing, as I said. Okay. So once we have the dust, we can see how these things should look like when you observe them, because the dust is basically defining your radiation transfer. First, one note on the spectral energy distributions, because that's what we normally use to plot essentially the emission of these. The continuum emission of the young stellar objects as a function of wavelength. We don't use the normal way of plotting the flux as a function of wavelength. And the reason is very simple. The reason is that if you do that, this is a typical star with disk, and from the optical to the infrared and the millimeter, it seems that this star with disk is actually producing a lot of radiation at 100 micron. This is obviously not true. The source of radiation is the star, and in fact, if you want to have a clear view of where the radiation, where the energy is coming and who is reprocessing, you should plot the energy, and that's why we normally plot nu f nu, which is basically this type of, it's the same plot, just multiplying by the frequency, or lambda f lambda, it's the same thing. And this is in fact showing you that if you take a decade, for example, so a decade in wavelength, delta nu times f nu is the energy that goes in that is being emitted there, and obviously most of the energy is emitted by the star, and only a small fraction is reprocessed by the envelope, okay? And this allows you to quickly see this thing, okay? Right. So essentially, this is way of doing allows to figure out how much energy is emitted in each decade of wavelength. Okay, how these objects look like if you do a radiation transfer. That's a star with a dusty envelope around it with cavities. What you see depends a lot on where you are looking for. Obviously, if you are looking in the envelope, you see a lot of extinction. You are reprocessing essentially all the stellar radiation is reprocessed in the far infrared by the dust. If you are looking through the cavity, you see the central object. If you reduce the opacity of the envelope and you increase the size of the cavity and you flatten your structure, so you are evolving from a core with a central protostar to a core with an inner flattened structure that starts to form a disk, if you want. Then you see that the spectral energy distribution changed. The importance of the far infrared is reduced. And again, if you go to an optically thick disk situation, so you don't have the envelope anymore, you just have this thick flare disk. Then again, what you see obviously depends very much whether you are looking from this direction or from this direction, because the opacity towards the central star changes very much. But basically, you see from most directions, you see the typical spectral energy distribution of a star plus a reprocessing disk. And if you reduce even more the amount of material that you put into the disk and you make it essentially mostly optically thin, also in this direction, then you see that essentially you see the star with a small infrared excess at very long wavelengths. Okay. Okay. This is a good point to stop. And my two, you can discuss whatever you like, but my two themes would be the pros and cons of using dust emission at infrared or millimeter wavelengths as traces of the circumstellar material, and why are ices and their processing important for the discussions that we are having. But obviously, feel free to discuss whatever you like.
Okay, take 5 minutes.
Now it's working. Okay. So I was saying at the time, the phrase was that protostars were the holy grails of infrared astronomy, but eventually was really an holy grail for infrared astronomy because they are too faint in the infrared to be observed there. So actually, they were finally identified in the sub-millimeter by the fact that they still have a huge cold envelope that is reprocessing entirely the radiation from the gravitational collapse. So as you move from a prestellar core to a protostar, a collapsing protostar, a young stellar object which still is undergoing accretion from the envelope but has started to form a disk and then a star with a disk and an evolving disk and eventually disappearing disk, what you expect to see based on those radiation transfer simulations that I showed you earlier are essentially a spectral energy distribution that moves from being very cold, essentially an approximate isothermal thing at 10-20 Kelvin, and moves all the way to being something, again, an isothermal thing at few thousand Kelvin. And in between, you have the various emissions. And the way they are classified is based on the slope of this spectral energy distribution, essentially, not in surveys. And Mike may remember this plot from one of his earliest papers. This was essentially exemplifying exactly what I'm saying now, looking at the near-infrared excess. If you look at the colors, the near-infrared colors, so essentially the ratio of the fluxes that you observe in the near-infrared between 1 and 3 microns, essentially in this case, in these two plots, the photospheres are very well localized in the loci of photospheres. If you add reddening from very cold dust, so dust that is far away and is not heated significantly by the radiation, but just absorb the radiation, this would move in this direction, these dashed lines. And if instead you add hot dust around these photospheres, so dust that is close to the star and is heated by the stellar radiation, then it would move in this direction across in the locus of the infrared excess sources, which becomes more and more clear as you stretch toward the longer wavelengths. So here in the traditional near-infrared 1 to 2.5 microns bands, they are still very close to the photosphere. When you go to 3 micron and beyond, the excess becomes more important and you see it more clearly. These were the original thing, and the reason why surveys at infrared wavelengths of star-forming regions were so important to derive, a census of the objects in the different categories. So this is this view graph is an example of one of the legacy projects done with the Spitzer satellite that was essentially observing in the mid-infrared range from 3 microns up to 24 microns. And this is how some star-forming regions appear. The contrast is not great, but these are some of the nearby star-forming regions as observed by Spitzer. When you see essentially various things, so you also see the emission from the interstellar medium, essentially the small dust grains that are emitting in particular features, but this is not the topic of today, so you can forget the extended emission and look at the point sources. If you look at the point sources, these are tracing the young stellar objects. The blue one are the one with disks, once you do the classification, as you will see in a moment, which are relatively are concentrated in a few locations, but are more widespread than the red one, which is the one that are the so-called class ones, so the one that are still accreting with a disk, but still accreting. And even more concentrated here are these green ones that are very few and concentrated on the high density peak, which are the what are believed to be the collapsing protostar in the main accretion phase. Okay, this again is an enlargement on one of these clouds on the raw fucus cloud, and you see basically the molecular gas and the point sources. The one that are highlighted in green here are the class ones, so the one that have still significant accretion from their envelope going onto the disk. And you see that they are concentrated on the high density peak, a little bit clustered, and yeah, well, surface density is not really important, but they are clustered, while if you look at the ones with disks are a little bit more distributed. Those that don't have the envelope anymore, just have the disk, are more distributed across the star-forming region, which is also telling you, by the way, that is a slightly older population that has had time to move around. If from those surveys, one of the most important results is the census, if you want, of the objects in the various phases, which is what you have here. In blue are the stars with disks. In green and are the transition stars, the one that are with an envelope that is being dissipated, and in red are the one with the envelope that is still accreting on the disk. So essentially, these are the youngest. These are the transition between the youngest and the disk, and these are the ones that don't have evidence for infrared excess. So they are the ones that are without disk. And the critical thing from these surveys alone is difficult to measure the exact number of these, because they look just like background and foreground stars, and you need to use different methods to identify them if you want to get correct statistics. But what can be done to have an idea of the different duration of the various phases from the protostar accretion, which is not here, which is not shown here, the protostars, the class ones, so the ones that are still accreting from the envelope onto the disk, and the one with the disk. Okay, you can just compare the number of objects in the different classes in the various star-forming region, and this very roughly gives you an indication of the time scale between the various phases, assuming obviously a constant star formation rate, which we know is not the case, okay? But to get a rough estimate, you can use this approximation. And if you use this approximation, you figure out that the stars with disks, the so-called class 2 objects, the blue ones, live for about 5 to 10 times longer than the class ones, the ones in which the envelope is still accreting onto the disk, which again are a factor of 5 to 10 more numerous, typically, than the real protostars, the ones that are still deeply embedded and accreting. And roughly speaking, you can get to this order of magnitude numbers. These are very order of magnitude numbers, based on the theoretic. If you can look at this two ways. I'll tell you first the first way you can look at this. You can have an estimate of how much it takes to actually form a star, so to accrete the material onto the star, based on the theoretical arguments of a collapsing prestellar core, which is of the order of 10 to the 4 years. So if you assume that 10 to the 4 year is the age of the class 0 objects, roughly speaking, then you propagate these fractions, and you get that the typical time scale for this phase is of the order of 10 to the 5 years, and or a few 10 to the 5 years, and the typical time scale for the class 2, so for the disk phase, is of the order of a few million years. Okay, that's a very rough estimate. The other way to get these estimates is to work in the other direction. So try to get an estimate of the age of the lifetime, if you want, of the stars with disk. And this you can do if well, before doing that, I wanted to show you how that is done, how that classification is done. And it's done essentially the same way as I mentioned before. So you have the photospheres, stars with disks and envelope-only objects are well separated in these color plots from Spitzer. So that's how those statistics are derived, essentially looking at at not only the slope, but the slope and curvature, if you want, of this portion of the spectrum, of the infrared part of the spectrum. Okay, going back for the time scale, sorry for this distraction. if you essentially estimate how many stars, how fast the star lose their disk, you can estimate the lifetime of the disk. And to do that, this plot that was shown already by Phil is basically based on these Spitzer surveys. This is counting the frequency of stars with infrared excess. So how many stars with infrared excess you have in a cluster, so in a star-forming region, of a given age, okay? So obviously there are two tricks here. It's easy to count the star with infrared excess because I showed you that it's fairly easy to identify them. What is not easy to do is to assign the age, as we discussed yesterday, okay? And the age, basically, in this type of graph normally is done by looking at the entire stellar population and trying to fit a pre-main sequence isochron to the population of pre-main sequence star. Okay, so that's the way it's done, that you get the age. The other thing that you need, and it's not trivial to do, to get to this fraction, is obviously you need to know what is below the fraction. So you need to know the total population of the star-forming region, because it's easy to identify those with infrared excess, but those without, it's not that trivial. And to do that, normally there are surveys for activity. And this means that since young stars, as I mentioned yesterday, are more active than the chromosphere of the star, are more active than main sequence stars. So they, the members of a star-forming region stood up essentially in an X-ray image, for example, because the young stars are the ones that have X-ray emission, and the foreground and background objects don't have X-ray emission. Or you can look at H-alpha surveys, so emission of for chromospheric H-alpha emission. And again, the young stars have a much higher emission in H-alpha than non-young stars. Okay, so this is how the population of, say, naked photospheres, essentially objects without an infrared excess, are determined in this star-forming region, which is uncertain. Now, I mean, this census will become much more accurate in the nearby star-forming region with the advent of Gaia, because obviously you can separate this population, the population of the members, kinematically from the foreground and the background population. And so that will be another important way of doing this, okay? So these are the key caveats with this diagram. The other basic caveat with this diagram is that is based on infrared excess, obviously. And infrared excess is very easy to produce by dust very close to the star. No, but does not tell you essentially how much dust there is around that young stellar object, because most of the mass is in cold dust that is not participating in this infrared emission, and this infrared emission is typically optically thick, by the way. So this is essentially a measure of stars that still have an inner disk, okay? Right. If you have a disk, again, this was shown in some way by Phil. The emission from a star plus disk, as you have seen before from the radiation transfer, is has a range of temperatures from the stellar photosphere down to the millimeter wavelengths and the cold dust in the outer disk. So it's well approximated the emission from a system like this, star plus disk, by a superposition of thermal emission at different distances from the star, corrected by the optical depth at that wavelength in the emission. Okay, and so essentially you can see that if you are in a situation, you can basically rewrite this in such a way that if you are in a condition which the emission is optically thin to the radiation, then the emission at any given radius is proportional to the amount of mass that you have at that radius times the temperature that is at that radius times the optical depth, the dust opacity coefficient at that radius. Okay, so if you have the same dust throughout the entire disk, so the dust opacity is the same in the entire disk. This does not depend on the radius, and the flux that you are observing is essentially proportional to the mass and the temperature. If you have an isothermal amount of dust, the emission, if you are optically thin, just depends on the total amount of mass and the temperature, as I was saying before, and the dust opacity, obviously. Okay. So to measure essentially this is telling you that to measure the mass of these disks, you cannot rely on the infrared excess, because in the infrared, these disks are optically thick, and this relationship does not work anymore. You really need to go to longer wavelengths where the emission becomes optically thin, and you can probe directly the mass into the disk. So if you look at it this way, this is just a sketch to show you what you can probe at which wavelengths when you observe a protoplanetary disk. So when you look in the optical, you mostly look at the scattered light from the surface layer, the tau equal 1 surface layer. If you look at the infrared excess, is not shown here, but when you look at the infrared excess, you are really looking at the hot emission from the inner disk. And when you go to longer and longer wavelengths, you start to probe deeper and deeper into the disk and farther away into the cooler regions of the disk. And at sub-millimeter and millimeter wavelengths, you are essentially sensitive to the entire disk, because the emission is essentially optically thin throughout most of the disk. Okay. So that's the reason why to study really the disk structure and the processes that happen on the disk midplane is important to go to sub-millimeter wavelengths, because you cannot probe them essentially at the other wavelengths. So the take-home point from what I said today, and that part I will discuss tomorrow. So tomorrow morning we look at the millimeter emission from the disk and what we can learn looking at the millimeter emission on the dust continuum emission in the disk. The take-home point from today is that dust is an excellent probe of the circumstellar material. It's easy to detect in the infrared, so it's easy to get the statistics of the sources, but tracing the total mass, one has to go into the millimeter because of optical depth, essentially. Dust opacity depends on the dust processing. So features related to grain growth, features are related to grain growth and composition, so the 10 micron feature, for example. And the long wavelength opacity trace the growth to large pebbles, as I said. So it's important to trace the first steps that were discussed yesterday by Willy of the formation of planetesimals. And we will look at this in more detail tomorrow. The near-infrared or mid-infrared even surveys provide an excellent census of these classical disks, of all the disks. And so they are the right starting point to study disk evolution. We will get to transition and evolve disk at some point, but not tomorrow. Okay, we will get to that after, when we discuss disk evolution. Millimeter observations are required to probe the bulk of the disk, and in particular to probe the midplane and the processes related to planet formation. Okay. I'll repeat the question.
Is there any wavelengths where we can probe only the midplane without the surface layers of the disk?
No, because that always gets into the way. What happens in reality is that at millimeter wavelengths, you are mostly sensitive to the midplane, okay? Because as Phil has showed yesterday, yes, the density distribution is a very strong function of the scale height. And so essentially, when you look at millimeter wavelengths, since you are probing mass times dust opacity, you are actually tracing mostly the midplane. But you always take into account also the surface, but you are mostly dominated by the midplane, where most of the mass is. Mm-hmm. I would need to go. I have to admit that I would need to go and check back the. So the question is whether the ages have been the ages. No, that's what you meant. The ages have been determined by all by the same people, and I would need to go back to the Hernandez paper. I have to admit. I think that many. Yes, because Hernandez basically what he did, he assembled data for himself from his own group, and those are all consistent. And data from the literature. So I'm not 100% sure what he did. 100% sure what he did with the literature. I have to admit that I need to check back. Yeah.
When the NR color diagram when you're separating, so we saw that in the previous plots that the inclination angle also or the scattering can also determine the slope. So how much contamination can these classifications typically have?
Okay, so this you can see here because so the question is how much the classification depends on the inclination angle, and it does a little bit, and you see it here because basically what is coded here in color are the different inclinations. So you see the various line of sights, no? And basically when you are, but I mean, it doesn't depend enormously. The region where it depends mostly is here if you want, okay? Because in class zeros, most inclinations are equal, except if you are unlucky and you look through the, through the cavity. But this, basically, if you assume random orientations, is a very small effect. It can be more important, and the same is true essentially here, because only when you have a disk really edge-on, you have a problems in classification. So, and there are cases in which they have a spectrum like a class 1 or even a class 1 mostly. They have a spectrum like a class 1 in the infrared, but when you do the image, you see essentially the disk absorption through the thing. But they are very few. Okay, and so essentially when you look at these general statistics, a few misclassified cases doesn't create a problem typically for the general rule. Obviously, individual objects may be misclassified.